If you're trying to figure out how to actually integrate AI across your software lifecycle, not just in one-off projects, QCon AI in New York this December 16th and 17th might be worth checking out. The entire conference is focused on the real-world side of scaling AI. You'll learn from technical leaders, senior engineers, and architects who've already been through it, the patterns that worked, the ML ops pipelines that scaled, and what they do differently. The conference is built for senior practitioners who need actionable blueprints, not just buzzwords. Learn more at QCon.ai.
Hello everybody, I'm InfoQ Pop, an InfoQ editor, and I have in front of me Marina Moore. Marina is involved with a bunch of stuff in the security space, more particularly platform and Kubernetes. But without further ado, I would like to invite her to introduce herself. Marina?
Thank you so much for having me. Yeah, so I'm a research scientist at Adera, a company that does hardened runtime, making your containers secure, the security boundary that Kubernetes was missing. In addition to that, I'm one of the co-chairs of the TAG Security and Compliance. That's the technical advisory group under the CNCF that advises CNCF projects on security and compliance. We do security assessments of projects and kind of just answer questions when projects have them to try and improve the security of the ecosystem overall.
Very good hats you're wearing. Thank you for helping the community learn how to be safer. My feeling is currently that containers are a very broad category. It started with the virtualization a long time ago. That was the natural step from bare metal to virtual machines. And then some people understood that there are things in Linux that can help with making things even more efficient. And then one thing led to another. And then we had containers, and then Docker stole a lot of the thunders for everything. We didn't hear that much. It works on my machine. And then we had Kubernetes as an orchestration solution, and other things appeared in the meantime as well. So maybe it's a good idea to define containers and to just create the context for our conversation moving on. So what are containers for you?
So I think the way I would define it is a container is a kind of a unit that packages up code and everything that you need to run that code. It's kind of like an abstraction over your program, right? Because if you just write the program, you can compile it or not, and then it runs on your machine. And a container puts in all that other stuff on your machine that helps it run on your machine, right? So it's not like a whole operating system or anything, but it's all those pieces of the code that you need to solve the it runs on my machine problem.
So basically what you're saying, a container is actually a container, right? So you have the host operating system, and on top of that, you have processes that contain your code, and then they act like isolated units, right?
Sort of, yeah. They kind of act like processes on the computer, which have some isolation properties, of course, just on their own, right? They run separately on the CPU and stuff like that. But they are sharing kind of the memory and that host operating system kernel.
And if I remember correctly, what you were mentioning earlier in your presentation is that actually it's not always that isolated as we would like for us to think.
No, yeah, I think the name can be deceptive sometimes because, it contains your code in that it has everything you need to run it, but it doesn't really contain it in that it fully separates it from everything else on that same operating system. Right. So if you have multiple different containers on the operating system, if there's no other things in place, and I think most times people use at least some sort of isolation properties on top of the container, but without those, you could just list processes running in other containers or do other things. Right. So on its own, the container doesn't actually provide that isolation boundary.
Is this related to the container itself, or is it related to one of the technologies? What do you think? This risk is predominant to all types of containers or Docker, to just single out one?
Yeah, I think it's kind of inherent to all of them. I think that people have done a lot of work to solve this problem, right? There are things like namespaces, C groups, setcomp that have become pretty standard across the industry to solve pieces of this problem, right? And all those technologies I mentioned, and there are others, they're ones that kind of run in user space, right? So they're also on top of that operating system that we're sharing between these different containers, but they just kind of provide boundaries. Like they say, these resources should be shared among containers in this way, or these containers should only be able to access these system calls or other kind of protections like that.
And what do you say if we run a bit through all of the risks? Now, how would you prefer to just look at all the risks, and then what would be the the wiser approach as you had it in the presentation, or we just look at all the risks and then we'll just dissect all of those?
Either way, yeah, we can look at all of them.
Okay. So what are the risks that we as developers encounter while running containers? Because while it's on our machine, it's okay. But after that, I think in production, it's a lot more interesting for malicious actors to try to get more out of it.
Exactly, right. And so when you're testing it on your local machine and doing stuff like that, the isolation that you need is different. And we can talk about Apple containers later, which I think they have some really interesting properties that they added to Apple containers so that even on your own machine, you could actually get some isolation for stuff that you're running. But regardless, when you have a container and it's actually in production, you might have sensitive data on it, right? You might have customer secrets, you might have other things like that. You might be running your container on shared infrastructure. So what's called multi-tenancy is where you have multiple containers either from different companies on the same machine or from different customers of the same company, right? Running the product in different containers. It's great for efficiency, right? If you can share the infrastructure, hardware can be expensive, compute time can be expensive. And so if we can share that compute time and optimize the use of those resources, this is great, right? But unfortunately, if you're sharing that infrastructure between these different containers, what this means most of the time is that you're sharing that operating system kernel, right? And so if you have different containers running in a multi-tenant way, but from different companies, say, and one of them is able to look at the memory, because it's like the same memory space, right? In this user space on the kernel. And so if they're able to access that memory, they can maybe see secrets running in the other container, or maybe even escape out into that operating system kernel and start messing around. And that's really what the risk is, right? So once you have this shared infrastructure, you have to make sure that not only is the stuff in a container, but you have some kind of boundary around that container to make sure that an untrusted workload in the container can't get out and affect other things. And also that your container is protected from all those other random companies' workloads that are on the shared infrastructure.
Thank you. And what should we do? Because, even though we have LLMs now to solve all of our problems, I still rely on human intelligence. So please guide us.
So I think there's a lot of things we can do. And there's a lot of different solutions that are out there on the market for what we can do. I work at Adara, and I think we have a great solution that's kind of in the VM-based isolation space. And the nice thing about that VM isolation space, and there's a lot of open source technologies in this space as well, is that it provides a really clean boundary, right? So instead of having that shared operating system kernel that you have to kind of put a bunch of band-aids on to try and isolate resources between containers, things like namespaces, cgroups, all that kind of stuff that, tries to define the boundary. The problem with all those band-aids is that they're still running in the same kernel. And what we've seen with a lot of what are container escape CVEs is that they're basically attacks on that Linux kernel, which means that if like one flaw in the Linux kernel, which is a huge piece of software, very impressive piece of software, but all software has bugs. And if a flaw there can mean that these protections can be overwritten by attackers, and that means that your containers aren't safe. And this is why I like the kind of the cleaner boundary of the VM-based isolation, because it means that you're eliminating that whole attack surface of the shared kernel, right? You now have different microkernels for each container.
So did I hear that right? One of the easiest solution or the straightforward solution would be to drop containers and go back to virtual machines?
Sort of. I think that the abstraction of containers is still really useful, right? And so I think that's where this kind of world of micro-VMs has come in, and having these like VM-compatible container runtimes. What this basically means is that you get all the kind of convenience of containers, right? You still get all the abstractions around it, all the tooling that Kubernetes and other systems have built. But under the hood, there's like secretly a virtual machine in there doing the isolation. So sort of yes, in that, we're adding that virtual machine back, but there's technologies that have made them a lot more efficient and also let developers themselves keep this abstraction of containers, right?
Okay.
And then all it's different is the infrastructure.
Let me see if I get the parallel. Some time ago, around a decade ago, we decided that microservices are the better approach to the monolith. Now, 2 years ago or 3 years ago, we decided that the monolith is a good option for most of the cases, but we call it a modulith. So now I hear you saying the same thing. We left virtual machines, we went to containers, and now we're going to micro virtual machines. Okay, fair enough.
Exactly. We take the lessons from both sides, right? Take the best of both worlds.
So to single out what you're saying, to just underline it, we are a technology group. We are a group of professionals that are very dependent on the "it depends" phrase. So we have to be very careful what type of technology we use when. And then in the cases when it makes sense to use the containers as they are, but then when situations require it, to use micro virtual machines, because they have the added benefits of the containers, but in the same time, they allow us to have the proper degree of isolation that we need, so not to have issues on the kernel level, right?
Yeah, exactly. And I think this is especially important, right, when you have these multi-tenant applications, these sensitive workloads running in them. I always hesitate to say that there's like one solution for everybody, but I do think that, when you need that isolation, the micro-VMs are a really good way to go.
Okay. Funny enough, I had a similar conversation starting from another point a couple of weeks back. I spoke to a bunch of guys from Couchbase and a guy that was a consultant in this space, and they took it one level further. And what they said is that, why use the kernel at all? Just drop it, use WASM on top of the bare metal, and that's it. It's magic. What do you think about this solution?
Yeah, I think this goes back to that there's not one solution for everybody. I think that WASM is another great technology in this space that does some really great sandboxing. I think one of the big downsides of WASM, or one of the reasons that I prefer micro-VMs like in general, but I still really like WASM, is like it still I think has a really strong isolation boundary. But you do have to recompile your programs for WASM, right? It's not compatible with all this existing container infrastructure. And I think this is creates a barrier for adoption for a lot of folks who have their existing applications, their existing containers that they really like. That being said, I think I'm very curious to see where the work goes, because I do think that it's moving in a similar direction, right? It's saying, let's make a better sandbox, right? Let's make a better box around our application.
Okay, so what I hear you say is WASM can be a solution, but probably it would be better suited for a greenfield project when you get started with it, because at that point you can choose, okay, you choose WASM and that's okay, you'll just compile the code. But on the other hand, otherwise you'll have to recompile everything, and that comes with the added cost. And on top of that, I suppose the different types of technologies, interpreters for WASMs, have different degrees of maturity, so that can be a risk in itself, right?
Exactly. Yeah. So I think that's why I'm excited to see where it goes. But I think that, for where a lot of people are today, I do think that sticking with something container related can be nice.
You mentioned micro virtual machine, micro virtualization. Can you single out some technologies? Because nowadays we don't use good old Google anymore, so we cannot Google for it. We have to ask an LLM, and these LLMs are hallucinating, as we know. So to make sure that we get some straight sources that we can try and not think that they're hallucinations.
Yeah, totally. So I guess to talk about technologies, I have to talk a little bit more about the stack of a micro-VM first. Just kind of understand how these things fit together. I think there's three main important pieces to understand about, sort of four. Anyway, main important pieces to understand about a micro-VM architecture. So you have some sort of hardware, and then you have a hypervisor that sits on top of that hardware that kind of manages the actual hardware, a little bit like an operating system would. And then you have what's called a virtual machine monitor, which helps allocate CPU and memory and other resources to individual virtual machines. So it kind of manages the different resources that go to the different virtual machines. And then if we're talking about containers, on top of that, you need some sort of container runtime, because you need something that can make this compatible with all of our existing container stuff. So going from the bottom up, at the very bottom layer, I think the two big ones to talk about, especially in the open source space, would be KVM and Zen. KVM is a module of the Linux kernel. So it's kind of like you just uses the Linux kernel to do all the hardware stuff that it already does, and then adds a module that allows it to be a hypervisor instead of just an operating system. This is really cool because it's compatible with a lot of stuff, and it uses what's called hardware virtualization extensions on most modern CPUs, which lets it kind of pass through the CPU in a more efficient way, right? Instead of having like a virtualized CPU, you get actual access to the CPU from these different VMs. This is very cool, but unfortunately, the access to those hardware virtualization extensions requires bare metal access to that CPU, or at least pass-through access if you're working on some sort of system in the cloud. So that's KVM. And then the other big one is Zen, which instead of being built on Linux is kind of its own standalone system, what we call like a type 1 hypervisor, right? Because it runs directly on the bare metal. And then Zen does also support what's called PBH mode, which does that hardware pass-through, but it also supports what's called para-virtualization, which instead of relying on the CPU extensions to do the hardware pass-through, it relies on minor tweaks to the guest operating systems to make what are called hypercalls instead of system calls in some cases, right, to access those hardware resources. So that's our very bottom layer, very like a quick overview of those. And then one layer up from that, we have the virtual machine monitor. A couple of big ones in the cloud space. Firecracker is a very popular one. AWS, Lambda, and Fargate. So it was originally created by AWS for those projects, right, to do that virtual machine management layer. And it's known for having pretty fast startup time. That's kind of like its big thing. Cloud Hypervisor is another popular open source one that lives at that layer. I guess I have to shout out my company also makes a Zen-based hypervisor at that layer as well. So sitting above that, you have to have some sort of container runtime. Kata containers, I think, is a very popular open source one. Under the hood, we have this virtual machine system, and it kind of translates that into what looks to everybody else like a container. Everyone above that the stack, like a container system. Those are the three layers, very briefly, of the hypervisor. And sometimes people call the whole thing a hypervisor, which is very confusing, but I like to separate them out.
Okay, so to just see if I got my lessons right, you have the kernel level, and you give as example the Linux KVMs. That's the base level, and on top of that comes the hypervisor. No, the other way around, right?
The hypervisor is that, KVM or Zen.
Yeah, it's the middle level.
Exactly, it sits right on top of the hardware. And then you have the VMM, which is like Firecracker, Cloud Hypervisor. And then you have the container runtime as the third layer.
Great, lessons learned. Thank you. Okay, so you mentioned Firecracker is quite fast, and fast is very useful these days because everybody is trying to pump up their ecosystem, if we call it like that, because, well, everybody's tending to have cheaper infrastructure, and then obviously we all want to be good citizens. Well, most of us want to be good citizens and have less carbon in the atmosphere. What does fast actually mean? Are we talking milliseconds? We are talking seconds, minutes? Where is Firecracker or any of them? I like the name. That's why I'm just picking on it.
It's a tricky question to answer because I think it depends on what you mean by startup time. So in the Firecracker paper, when they first released Firecracker, the number they cite, I'm going to get the number wrong. I think it's like 200 milliseconds or something. It's the Firecracker paper. You can find it to find the real number. But what they're measuring there is very specifically like the boot time of the VMM, right? That's specifically what they're measuring there. But they're not measuring the full time it takes for the whole stack to turn on, right? We just talked about all three layers of the stack. And if each of those took 200 milliseconds, that would add up. I think in my testing, I found if you do like an end-to-end, and of course it depends on your hardware to get exact numbers, but I think I found it to be closer to a second or so for the full startup of a VM using Firecracker.
That's good in my book.
Yeah, it's not too bad. And I think it can be tricky if you're turning on and shutting down machines a lot. And part of the argument they make in that Firecracker paper, though, is that you can do what's called a warm start. So if you know you're going to need a new container, you kind of pre-start the virtual machine layer, so you don't really lose that 1 second. Like the user doesn't notice the 1 second.
So how they used to do it in the good old JVM Java days when they just had to run it and warm it up and got it to be warm enough to just be at its most efficient execution time. Okay, great. Now I have a lot of links to read. Thank you for that. And because we used a lot of it depends. What would you say if we're looking at a couple of normal things that you'll see in normal architectures and then try to create some kind of matching? I don't know, let's say some kind of microservices, small scale, a couple of tens of services. What should I use? Should I go for that, or it's something that it has still another it depends level and we cannot single them out?
Yeah, I think there's a couple of characteristics of performance. And I will shout out here, I think I have a white paper for Adira that I can send and get linked somewhere because I have a bunch of graphs in that about these different characteristics of performance that have like real numbers in them, right? So that might be a useful resource. But I think in general, it depends on whether we're talking about the CPU heavy workloads, which I found don't tend to vary that much between different stacks in this space, versus the memory heavy workloads, which do have some variance. And the system call heavy workloads tend to have the biggest variance, just because the system calls by their nature have to pass up and down this stack a little bit more. And so the characteristics of that performance can differ more between systems. In that paper, I mean, obviously like running on something like Docker is the fastest, right? But then just because you're not adding these extra layers, you can get pretty similar performance with some of the other ones. Adair, I think, did pretty well in that testing. And I think I need to find my graphs just to remember all the different performance characteristics. But yeah, there's a lot more detail in those graphs.
Thank you. So it will still remain with it depends because it's actually more about the type of code that we are running into it rather than just putting it in the wrong buckets. So if it's something computation intensive that will use a lot of CPU, then that's obviously one of the choices that we should take based on that. Or if we are just writing a lot or these kind of things.
Yeah.
What else we should know as an industry about running safer containers?
Yeah, I think something that I've been thinking about a lot recently, I'm sure a lot of people have been talking about, AI recently, as I'm sure you know, is GPUs, right? GPUs in the cloud. And I think that this is definitely a growing space, especially as people start using GPUs, not just for training, but for inference in the cloud, which means that lots of different people are doing inference in the cloud. And not only do they need GPUs, they don't always need an entire GPU, right? They just need some time on a GPU when they're doing inference. And this has led to a really big rise in multi-tenancy for containers. Now we have multi-tenant containers also accessing GPUs, right? And so I think this is another really interesting space that kind of adds another layer of complexity here, especially because I think the GPUs, just because of what they were originally designed for, which was not really originally designed for AI, they happen to be very good at that, right? But the security characteristics, especially of running inference for different users on the same GPU, is not always great, right? They don't usually clear memory between different processes running on the GPU and other stuff like that, which means that there's a lot of challenges in this space of adding GPUs into this crazy mix of container isolation.
I was just thinking about one thing. For a long period of time, Kubernetes was the solution for everything. If you have a problem, just put Kubernetes in place. Well, Kubernetes is another type of abstraction that was on top of containers. In the whole landscape that we provided, where does Kubernetes fit in, if it fit in?
Kubernetes, I think, is very good at what it does. What it does is the container orchestration, kind of the scheduling of containers. And so I think it still really fits in at that level. And I think what people are starting to realize is that something that's good at scheduling containers might be good at scheduling other things too, right? So I've seen this a little bit more of people using Kubernetes to schedule other types of workloads, other types of activities. And one of the benefits of Kubernetes is not just that it's good at the scheduling, but just that there's this huge ecosystem around Kubernetes, right? I don't know the current number of CNCF projects, but it's in the hundreds. And these are all projects that are built around making stuff better for folks who are already using Kubernetes, right? And so not only do you get the great scheduling of Kubernetes, you get access to observability, security, monitoring, all this other stuff on top of that.
Okay. We discussed a lot about memory, and that's the main point, that they're sharing memory kernel. And probably the only legislation for cybersecurity that still remains in place in the US is memory-safe programming languages. That's obviously something that singles out Rust. Does it make a difference about the code that we run in the container? Does it provide the extra safety space for us, or that doesn't really matter?
I think it does matter. I like to think a lot, especially in this space, about the idea of an attack surface, right? So the attack surface includes, all the code that's required to run your workload. If you just have a traditional system, this would include the operating system and the container runtime. If you're running a micro-VM, right, it's that microkernel that's just unique to your container and maybe the hypervisor. And any vulnerabilities in that space matter. And what Rust does and what other memory-safe languages do is they just really reduce the likelihood and instances of memory errors. There's some paper that found that something like more than half of all vulnerabilities came from memory leaks, right? And so this is just a really easy way to, I won't say eliminate, but very close to eliminate a whole very common category of vulnerabilities. And that's one of the reasons at Adair we've chosen Rust to build that hypervisor level, because that's, the key part of your attack surface. And so having it in Rust just kind of makes it a little bit easier to trust that piece of the stack. And I think for most new projects, I think Rust is a great choice for that reason.
So it all boils down about the attack surface.
Exactly.
Keep your things simple, and that will make your life simple.
Yeah.
Basically, that's it. If we apply that rule of thumb for everything, that's obviously the best way moving forward. I like that. It's easy to remember.
Yeah, exactly. The easiest code to maintain is the code that's not there, right?
Exactly. Now, I was just thinking about the VPN solution that at some point we chose because of that. It was the simplest possible one. It had very small footprint. Is there anything else that we should have for our listeners, or that's a wrap?
I guess I could talk a little bit about kind of confidential computing and kind of going even one layer beyond this micro-VM based architecture, if that sounds interesting.
Well, we started the conversation saying that we store a lot of things, or we have a lot of things in containers, secrets and other information that usually PII that usually we don't want to leave the boundaries of the company. What should our listeners think when they hear confidential computing?
Yeah, I think the most important thing that confidential computing does is encrypted memory. For years we've known that it's great to do encryption at rest, encryption in transit, right? So the data can't be accessed in those places. What confidential computing adds is encryption in use, right? So in the running memory of the process, it can also be encrypted. And the way it does this is with what's called a trusted execution environment, which is a special piece of hardware that enables this encrypted memory in a somewhat performant way. So that if you run your container workload inside the trusted execution environment using something like the confidential containers project, or there's other projects out there, what you get is that you get that encryption in use. So that you don't, and we were talking about attack surface earlier, you don't have to actually trust your underlying operating system or anything that's not inside that TE, because you can encrypt stuff in memory and do what's called remote attestation to kind of prove the running state of the application in that TE. So I think that's the big thing, is encryption in use and reducing your trusted computing base or your attack surface.
So, as I mentioned earlier, we should minimize the attack surface, or the code that we have, to make it in the best potential way, right? Now I'm thinking, how should we take care of that? We're just thinking about developing and the developers writing their code and so on and so forth. And what we heard in the last 2 to 3 years is we are shifting left. Well, everything shifted left. Probably it's an overflow and we got to on the right side. Well, that's a whole different conversation. Are there tools that can help us diminish our attack surface? Well, I don't know. I'm just thinking about a tool chain that we can use as developers and trying to see and minimize it, optimize it, and so on and so forth.
Yeah, definitely. I think there's a lot of tools out there for kind of minimizing different layers of the stack. You can make your container images smaller. You can make your kernel, especially that microkernel, whatever, smaller. And I think that anything that you do that removes code reduces your attack surface and can make stuff more secure. My PhD advisor actually has a paper that he wrote about, it's called Lind, that talks about this, where basically in the Linux kernel, the most common vulnerabilities were from really rare portions of code. Like the code that's the least used tends to have more vulnerabilities because people aren't noticing the bugs, right? Because they're not using those portions of the code. So if you can kind of remove those less used parts of the kernel or of any other layer of the stack, then you can make it more secure. So that's, I think, a really great way to do that as well.
But that's something that theoretically should happen on the developer side. So for most of us, the operating system is something that we take for granted. We're just pulling it from somewhere and we're using it. Is there a solution for that? I don't know. Well, I'm just thinking now that in the Java virtual machine, there were moments when you had the code being optimized. And then, as you said, those beaten tracks were natively compiled so that they run faster. Do you know of anything that will help us do that?
So you're saying something that'll help us just make there be less code in the trusted computing base? Is that the point?
Yeah, that's the question. So for the operating system, as you said, there are parts of it. We're just taking the kernel as a whole. Most of us, we're just using part of it, or our applications use just part of it. We cannot go and chop it down or take parts of it out. Is there a solution for that? Do you know of anything that can help us in that regard?
There's a couple of different approaches here, right? So you can try and optimize it, like we were talking about, reduce the amount of code in it. I think that can be very developer intensive, but it can be very useful for reducing your trusted computing base. I think the other thing you can do is just put barriers in place to reduce the splash zone of some sort of vulnerability in one of those layers. I think this is something that things like container isolation, things like trusted execution environments are very good at, because you don't quite assume a vulnerability, but you're like prepared for it. If there is one, you can really limit what it can do, right? So if you, for example, have a container inside a micro-VM and do a container escape, and the attacker is able to do a container escape, they've now escaped onto their own machine with nothing else running on it. The attack becomes useless, even though you haven't prevented the attack. And I think that's a similar argument in confidential computing, right? Is that if you are able to only run your one small piece of trusted application in the TEE, and there's a vulnerability somewhere else in the stack, it has way less impact on your particular application.
Okay, so what we said until now is that minimizing the attack surface and our code, or all the code that we actually expose, being code that we write ourselves as a company, or the dependencies that we import, or whatever we use, it's one way of looking at it. That's one approach. And now what I'm hearing you saying is we should isolate the application in such a way that we diminish the blast radius. In case something happens, it's something that is contained rather than just affecting more components of our system. Is that right?
Yeah, exactly. This is, I think, a great way to say it, because it just affects less stuff, right? So I think that code will never be perfect, right? I think that's something that is always important to understand, that there always will be vulnerabilities. We can slim stuff down as much as we want, we can make it tiny, but we'll still probably, even if it's one line of code, there's probably some vulnerability in it, right? That's just the way it is. And so if you can just limit what that vulnerability can do, limit how bad it can be, I think that's a really good approach.
Thank you.
Yeah, thank you so much for this. This is a great conversation.